I'm going to denote by lambda k n the space of homogeneous symmetric polynomials of degree n in m variables, and this k is the field of coefficients, and we'll only be assuming that this k has well, let's see what we'll be assuming about k. But so I hope this is clear what this means to everyone. You just take polynomials in m variables, Sm, the symmetric group on n, m elements acts on it, and you look at the polynomials which are invariant under that action. And you can change the number of variables, so you can define a specialization map SPM which takes m, the thing over m variables, the thing over m minus 1 variables. Or, well, actually, so what you do is you take this last variable and set it to be equal to 0. And then what you have is a polynomial in m variables. So, oops. And for example, if you take a polynomial in which all the monomials contain the m plus first variable, then it will vanish. So this is not an isomorphism always, but it turns out that this is an isomorphism whenever m is greater than or equal to n. This requires a little thought, but it's not very difficult. In any case, I won't do it now. So I'll call this the stable case, and once the number of variables exceeds n, you can just identify all these spaces m plus 1, m plus 2, m plus 3, and you can just talk about the ring of symmetric, well, homogeneous symmetric functions in of degree n. So this will be the stable case. I'm a bit vague here, but what it means is that you just take any of these cases where m is greater than or equal to n, and you can change the number of variables at will so long as you stay within this range using these isomorphisms. So let's look at some examples of these things. So example 1 are power sum symmetric functions. Pn is just defined as x1 to the power n plus x2 to the power n plus xm to the power n. So this is a power sum, and given any partition mu equals mu1 dot 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 mu m. Now with partitions, if it has fewer than m parts, I'll just make it m by putting some zeros at the end. So we won't worry too much about that, but certainly this mu cannot have more than m parts. Well, I guess here it doesn't matter. So okay, so we get p mu to be the product p mu1, p mu2, p mu m, and if this is a partition of the integer n, then this thing, well, this will have degree mu1, this will have degree mu2, and so on. So this p mu will have degree n. This p mu is a homogeneous symmetric polynomial of degree n in m variables. And let's look at another example. These are the Schur functions. So these were defined by Cauchy as follows. Suppose you have integer vector alpha 1, alpha 2, alpha m, and we'll be assuming that these are non-negative integers. Then you can define an a determinant A subscript alpha as x1 to the power alpha 1, x1 power alpha 2, x1 power alpha m, x2 power alpha 1, x2 power alpha 2, xm power alpha 1, xm power alpha 2, xm power alpha m. So this is a polynomial in the variables x1, x2, xm, but it's not symmetric, it's alternating. If you interchange two of the variables, then its sign changes. As an example of this is take as alpha delta, which is m minus 1, m minus 2 down to 0. Okay, then A delta is just the van der Waals determinant. Which is the product over I less than j xi minus xj. Okay, but one way to get something symmetric out of alternating is to take two alternating things and multiply them or divide them. So what Cauchy did was the latter. So Cauchy defined S lambda to be A lambda plus delta divided by A delta, where lambda plus delta just means, you know, component wise addition. So lambda 1 plus n minus 1, lambda 2 plus n minus 2. This was Cauchy's definition of the Schur function. And it turns out that this is actually a polynomial, that these factors, it's not so difficult to see that those factors can actually be taken out of this. Okay, so one important fact is that these S lambdas, as let's assume that m is greater than or equal to n, then S lambda as lambda runs over all partitions of n is a basis for lambda. So I'll just write lambda k n. I won't put the number of variables, we are assuming that you take the stable case. So the Schur functions, they form a basis for this space of homogeneous symmetric functions of degree n. Okay, so you can take any symmetric function of degree n and expand it in terms of Schur functions. And a very important example of this is the Murnaghan-Nakayama rule, which says how to expand example 1 in terms of example 2. It says that P mu is a sum over all partitions. So let's say mu is some partition of n, and the coefficient of S lambda is the character of the representation of the symmetric group corresponding to lambda evaluated at an element with cycle decomposition given by mu. That means its cycle decomposition has the cycles are mu1, mu2, mu3, those are the sizes of the cycles. So in this case we are assuming that the characteristic of k is at least n. In that case the representation theory of the symmetric group Sn is semi-simple. I mean the all representations are completely reducible and the classical character theory goes through, or you can just take characteristic 0 if you like, but in any case this is the identities. So that nicely links symmetric functions with the representation theory of symmetric groups. Okay, I won't give a proof of this either today, but let's just take it as a for granted. You will find a proof in my earlier lectures online or in the notes. So Okay, so that's the Murnaghan-Nakayama rule. Okay, now let's just see a nice trick for computing how to expand something in terms of Schur functions. Before we do that, it's convenient to just define an inner product. Well, I should say a bilinear form. You just say S lambda S mu is delta lambda mu. The advantage of this notation is that if I want to expand something in terms of Schur functions, then I can write the C lambda as just the inner product of S f against S lambda, instead of always saying expand with respect to Schur functions and then take the coefficient. So that's the advantage of this. And so let's just say we have this kind of expansion. How do we find these C lambdas? So here's a nice trick for that. So take this expansion, then I can rewrite this as f a delta is equal to, just multiply both sides by a delta, C lambda a lambda plus delta. Right? Okay. Now both sides are alternating polynomials. Okay. The first thing to note is that if you have an alternating polynomial, you cannot have monomials like x1 squared, x2 squared. You can't have monomials where two variables are raised to the same power, because maybe even x3 to the power 18. Okay, so it doesn't matter what the other variables are raised. But if these two variables are raised to the same power, then you can take the odd permutation of this, just interchanging these two variables. This monomial remains the same, but because it's alternating, the sign of its coefficient should become negative. So the sign of its coefficient is equal to its negative, so the sign of the coefficient should be 0. So these sides only have monomials with distinct powers. And if you have any monomial with distinct powers, you can just permute it to get powers in strictly decreasing order. So if you just know the and then alternating says that, you know, if you know the coefficient of monomials in strictly decreasing order, you know the coefficient of all the monomials. So you just need to be able to compare the coefficients of strictly decreasing monomials on both sides to figure out what these C lambdas are. Now the next observation is that suppose we look at this A lambda plus delta. So let me just write it down here. So A lambda plus delta is x1 raised to lambda 1 plus n minus 1, x2 raised to lambda 2 plus n minus 2, and no, still x1, x1 to the power lambda m, and so on, x2 power lambda 1 plus n minus 1, x2 power lambda 2 plus n minus 2, x2 power lambda m, and all the way up to xm. Now if you expand this out using the as an alternating sum over the symmetric group, this is A lambda plus delta. Now suppose you expand this out, then you get a sum over the symmetric group of you take some, you take the I comma wi'th element and multiply them all, right? Now this lambda is a partition, so lambda 1, lambda 2, lambda m are in weakly decreasing order, which means that the lambda 1 plus n minus 1, lambda 2 plus n minus 2 and so on are in strictly decreasing order. Okay. So now how many strictly decreasing monomials are there in this determinant? Yes, this, sorry, thanks Kamalaksha, this n should be m here, yeah, otherwise it won't fit in the matrix. Okay, yeah, so how many strictly decreasing monomials? Suppose you start here, you cannot come back here, right? But when you're choosing your term in the expansion, you have to go through every row and choose one element. so that you can't really do if you start here. So you must start here. And the next stage, where can you go? You can't go beyond this because again you won't have enough room to choose what happening there. So there's only one strictly decreasing monomial here. And what is that monomial? Well, it's just coming from the diagonal. So this has only one strictly decreasing monomial. And that is x to the power lambda plus delta. So I am using this notation, which is probably not too difficult to decipher. This means x1 to the lambda plus n minus 1, x2 to the lambda plus lambda 2 plus m minus 2 and so on. So there is only one strictly decreasing monomial. So if you look now at this equation, what are the strictly decreasing monomials on the right hand side? There is one for each partition, right, and that is x to the power lambda plus delta, and its coefficient is c lambda. So c lambda is the coefficient of x to the lambda plus delta here. If we want to find out fs lambda, then this is coefficient of x to the lambda plus delta in f a delta. Let's try an example of this. Let's take a partition mu of n and take the Schur function s mu and multiply it by the Schur function s1. Okay, this s1 is a symmetric function of degree 1. It's a Schur function. It turns out to just be x1 plus x2 plus xm. This is s1 in m variables. Okay, s1, p1, they're both the same. Okay, so let's look at this s mu s1 and let's try to expand it in terms of Schur functions. Now this lambda will be a partition of n plus 1 because this degree has gone up. So we're just asking, how does this product of Schur functions expand as in terms of Schur functions? And well, this is actually equal to the coefficient of x to the power lambda plus delta in, so we multiply this by a delta, so s mu a delta is a mu plus delta, and then s1 is x1 plus xm. Okay, this is a strictly decreasing monomial, and how can I get so I take to get monomials in this product, I would take a monomial here and just increase the power of one of the x's by 1, right? Just take a monomial here and increase the power of one of the x's by 1. Now if I start with a monomial that is not strictly decreasing and increase one of the powers by 1, I cannot get something that's strictly decreasing. At best I can get something with 2 powers equal. So the only place where I can start is with x to the power mu plus delta itself and then increase one of the things by 1. So what you get is that the coefficient of this and this is either 1 if you can obtain lambda by adding 1 to one of the parts of mu. So I'll denote that by saying lambda belongs to mu plus. Another visual way of thinking about this is that you draw the Young diagrams of lambda and mu. If the Young diagram of lambda differs from the Young diagram of mu by just having one extra box, then you say lambda is in mu plus and 0 otherwise. Okay, so this is This is 1 if lambda is in mu plus and 0 otherwise. Let's look at another. Yeah, that's fine. Okay, so we'll leave this here and we'll come back to use it later. Now let's go on to construct the characteristic function of Frobenius, which is this talk is really about. This is a kind of Pieri-rule. We'll see another version of it, which is representation-theoretic. This characteristic function will help relate rules of this type and representation-theoretic rules. So now on to the characteristic function. It's just another way of looking at the Murnaghan-Nakayama rule. So in our new notation, we can write P mu S lambda is equal to, so the Murnaghan-Nakayama rule says if you take P mu and expand it in terms of Schur functions, you get the character values. So that's chi lambda W mu. That's the Murnaghan-Nakayama rule. Okay, now let me just remind you some basic representation theory. Let's denote by Rsn the space of k-valued class functions on Sn, and on this we define an inner product, well, a bilinear form I should say, f comma g Sn 1 over n factorial summation w in Sn f of, well, maybe I'll write it like this, mu is a partition of n, f of w mu g of, we would write w mu inverse, but it doesn't really matter, g of w mu. You can write an inverse, but in the symmetric group every element is conjugate to its inverse, so we don't need to worry about this. And this is the form with respect to which the irreducible characters form an orthonormal basis. Okay, so this is just that usual form. 1 over n factor, I want to normalize it. Oh yeah, I need something else, yeah. I need, yeah, you're right. So I need to multiply here by the cardinality of the conjugacy class mu. Thanks. So this just denotes the cardinality of the conjugacy class mu. And that actually has a nice expression because this is n factorial divided by the centralizer of an element of cardinality mu, and so this you can write as 1 over summation mu and 1 over z mu. This is the cardinality of the centralizer of an element of with cycle decomposition mu. Okay, so now this I can write in terms of this form as follows. So chi lambda w mu is nothing but if I take the characteristic function of the conjugacy class corresponding to mu and take the bilinear form evaluated against chi lambda, then I'll get some scalar multiple of this, right? So let me go to the next board. So P mu S lambda is equal to chi lambda W mu, which is equal to, so if you take the characteristic function of the class of mu and multiply and take its this bilinear form against lambda, then you don't quite get chi lambda W mu because you're adding over the whole class. And the thing is anyway divided by n factorial. So what you get is z mu times this, right? So so you can rewrite that as p mu by z mu s lambda is equal to the inner product, the bilinear form of this. Now any class function can be written as a linear combination of these things. So if you have it's 1 by z mu, because I just brought the z mu over to this side. Yeah, so that's the class. So this is actually, maybe I should write it. So it's n factorial, and then I must divide by c mu, because the form has an n factorial in the denominator, and I'm summing over the whole class, but I only want one of the points, so I should divide by c mu, and that's z mu. Okay, confuses me all the time too. So z mu. So this is the identity you get. The inner product of p mu over z mu against s lambda is this. Here probably I should write Sn. Yeah. So this one is on symmetric functions, where the Schur functions form an orthonormal basis, and this one is the one that's used for Schur's orthogonality relations. Right. So now if you have the general function f, then what you find is that f chi lambda, well, f can be written as summation mu is a partition of n, f w mu, and then 1 sub c mu chi lambda. But then 1 sub c mu chi lambda is p mu by z mu. Sorry, not, yeah. Is something wrong? Yeah, that's okay. Yeah, and here I should write s lambda. It's just using this thing and linearity. So this this is what is called the characteristic function of f. So the characteristic function of f, this is what Frobenius called the characteristic function, is by definition the sum over all partitions of n, f of w mu, p mu by z mu. We assume that f is a class function. Okay, so what this tells us is that hang on. So this is a map from class functions on Sn to homogeneous symmetric functions of degree n. It takes k is a field. Yeah, maybe I should have put a k here also, but okay, and we are assuming that the characteristic of k is greater than n, or greater than n, yeah. Okay, and what this does is that the characteristic, if you want to compute the inner product of f against chi lambda, then what you do is you compute the characteristic function of f and you compute its inner product against s lambda. Now here's a nice observation, that if you take chi mu against chi lambda, well, Schur's orthogonality relations tell you that this is 0 if lambda is not mu, and 1 if lambda is equal to mu. But this is the characteristic function of chi mu against S lambda. But delta lambda mu is the characteristic function of S mu against S lambda for all lambda and mu. So what you can conclude is that the characteristic function of chi mu is S mu for all partitions mu of n. So that's another nice property of this characteristic function. It takes the irreducible characters to Schur functions. And of course the other thing you get is that if you take FGSN, then this is equal to characteristic function of F. It's an isometry, so to speak. Just because this is true for irreducible characters chi lambda chi mu, it's true for bilinearity for every function. So you can see that it's an isometry from this space to this space. Okay, let's now apply what we have learned to. So we'll use this thing, what we'd like to call a Pieri-rule, to derive another thing that's called Pieri-rule. So what we want to do is we'll start with a partition of n plus 1. We'll take irreducible character of Sn plus 1 corresponding to mu. So take mu is a partition of n plus 1, take chi mu. Does this inequality have a name? I guess it's you could call it no, I mean it's pretty close to the Murnaghan-Nakayama rule, so I guess it doesn't have a separate name, not that I know of. But this is what really makes this characteristic function work. Like this is the one place where you suddenly realize, I should define it to take this thing to this thing and extend linearly. This is where you realize how it should be defined. So this is a very important step. Okay, coming back to what I was saying, let's start with the partition of n plus 1. Look at its irreducible character, and by putting this downward arrow, I will mean that I'm going to restrict it to Sn. Okay, so this is an irreducible character of Sn plus 1. I'll just restrict it to the subgroup Sn of Sn plus 1, which is just the group which permutes the first n of n plus 1 symbols. And well, how do you compute that? So if mu is a or say let's say if eta is a partition of n, then this is chi mu. I'll use this notation w eta comma 1. Which just means that you take this partition eta and append a 1 to the end of it. Well, if it has some zeros, then you please append the 1 just before the last, the first 0 or just after the last non-zero term. Okay, and that's clear because of the way Sn is sitting inside Sn plus 1. It's the last element is the cycle all by itself. So. And this, by the Murnaghan-Nakayama rule, is P eta P1. This is where the the power sum symmetric functions are defined multiplicatively. So this becomes really nice. It's just P eta P1 S mu by the Murnaghan-Nakayama rule. Right? It says that you should take P of whatever class you're computing it at and go against the Schur function of the representation. Okay, so let's keep that in mind and let's try to compute what the goal is, I have this representation of Sn plus 1, I restrict it to Sn, I want to know how does it break up, what are the irreducible representations occurring there. And so what you want to really compute is this, right? And now we know how to do this. We'll compute the characteristic function of this and take its evaluate this bilinear form against the Schur function. And to compute this, all we need is this formula. So 1 over z eta p eta p1 s mu. That's the value at w eta w eta, and so we need to multiply it by p mu by a p eta, sorry. And then take the inner product against S lambda. This is just the characteristic function of the restriction of chi mu to Sn using this formula that its value at W eta is this. Okay, and now comes the clever part. The clever part is to take this in here, anyway these are scalars, and then to take this fellow out. And put this z eta also against this. So 1 over z eta p eta s lambda, and then we have p eta p1 but p1 is the same as s1, and then we have s mu. Okay, maybe I so now this S1, it can be taken outside this sum. So it's all this junk times S1. That's a p eta, by the way, it looks something funny. But what is this junk here in the brackets? This looks like a characteristic function, right? It's something by z eta p eta. So what is this something? This is the coefficient in the expansion of p eta in terms of Schur functions. So this is actually the characteristic function of chi lambda, and therefore this is S lambda.
How do we check this last, the step before the last to the last step?
From this step to this step, this step to this step, this step to this step, well, if you want, you bring this in here. Then you so then you can write this as 1 over z eta p eta s lambda, and then you bring this out next to it, and then use linearity to take it out again. Okay, so it just uses linearity of the bilinearity of the form, and that is just S lambda, right? That's characteristic function of chi lambda. So that's S lambda S1 S mu, and that we had on this board here. This is equal to well, it's slightly the notation has gotten reversed, but let me just write it here again. So we know that this is 1 if mu belongs to lambda plus and 0 otherwise. Or we could write 1 if lambda belongs to mu minus and 0 otherwise. This is the same as saying that mu belongs to lambda plus. Okay, that means that you can take the Young diagram of mu and remove a box to get the Young diagram of lambda. So this is the this Pieri-rule and this Pieri-rule, that if you take the representation chi mu corresponding to mu and restrict it to Sn minus 1, it breaks up in a multiplicity free way into precisely those representations corresponding to partitions which you obtain by removing a box from the Young diagram of lambda. So that's the other Pieri-rule. Okay, so that's one way to use this characteristic function. And let's do. Okay, so why is this equal to S lambda, right? So what is this value? This is really chi lambda W eta. So what you're looking at it as is summation 1 over Z eta chi lambda W eta P eta. That's the characteristic function of chi lambda. But the characteristic function of chi lambda is S lambda. So that's okay.
Orthogonal basis with norm Z p. So if you look like that, eta divided by Z p.
Yes.
Eta, they form it's almost orthonormal. So this is the expression of S lambda with respect to that basis. It's S lambda p eta.
So you're suggesting that we interchange the roles played by.
You just work purely at the level of symmetric groups. You don't need to bring in the Murnaghan-Nakayama once more. You work at the level of symmetric groups. And S lambdas are an orthonormal basis. The p etas are an orthogonal basis.
Okay. So what you're saying is these are an orthogonal basis. So if you want to write down anything in terms of the p etas, then you would take its projection against each of those, which is this term, and then
Divide by norms.
yes.
Norm square is Z eta. I mean, one needs that addition.
But I didn't. Is it clear somehow that the p etas are orthogonal from just what I've said, or certainly from that? But maybe from this you can deduce it again. So yeah. Yeah, so probably from this you can deduce that the p etas are orthogonal with inner product given by I guess 1 by Z eta or Z eta, yeah. Okay, so we can take this game and play it a little harder and get another nice result. Which is about what are called Littlewood-Richardson coefficients. One way to define Littlewood-Richardson coefficients is this. So you have three partitions. Let's say mu is a partition of M, nu is a partition of N, and lambda is a partition of M plus N. Okay? Then you take S mu, S nu. This is a homogeneous of degree M, this is homogeneous of degree N. So this product is homogeneous of degree M plus N. So you can ask, okay, what happens if I expand it with respect to Schur functions of degree M plus N? And the answer is, well, the coefficients are these things. I mean, it's not an answer, but the name of these things is Littlewood-Richardson coefficient. So that's one way of defining Littlewood-Richardson coefficient. But we'll see now a representation-theoretic interpretation of them, which will show that these are non-negative integers. Okay, from here it's not clear really why they should be non-negative integers. Well, most of you probably know about yet another interpretation of Littlewood-Richardson coefficients in terms of tensor products of representations of general linear groups and so on, but let's just pretend we don't really know anything here. and I'll do that. So what we've seen is an example, I mean this is a special case of this. What we're saying is that C mu 1 lambda is equal to 1 if lambda, oh, all my lambdas and mu's are mixed up. Anyway, this is what we proved.
So what you are saying is that if I just purely use the symmetric functions, it's not requires proof that it's not.
It's not clear if I just multiply these things why it should be non-negative. I mean, on the face of it, the way the inner product has been defined, it seems to have very little to do with the multiplicative structure of symmetric functions. We just said the Schur functions are an orthonormal basis, and it somehow doesn't seem to even relate different degrees or anything. So it's definitely not clear why this should be anything nice. But this has a representation theoretic interpretation. And so for this, what we need to do is we need to extend the characteristic function to the product of two symmetric groups. So you take the class functions on Sm cross Sn, and that's nothing but you take the class function on Sm and tensor it over K with the class functions on Sn. And so you define the characteristic function, I'll call it m comma. So if you have a function here and a function here, then you can talk about a function on the product, maybe w comma v, f w, g v. So a tensor, an element in this tensor space gives me an element here, and that gives an isomorphism of these two vector spaces. So this characteristic function now I'll just extend from this space to, well, the right hand side I won't simplify at all. I'll write R K M tensor K N. Okay, now this M is not the number of variables anymore. We've forgotten about the number of variables, just saying that there's enough variables to do whatever calculation we are doing. So this M is now at par with the N. So this is, I just define it to be the tensor product of the characteristic functions at the mth and nth degree. Okay, and there are two things that emerge from this if you just work out the details. And the first is that if you look at this, then you can ask what it is in terms of this interpretation, and it turns out that it is, you take a partition theta, sum over partitions theta of m, sum over partitions eta of n, 1 over z theta, 1 over z eta, f of w theta, w eta, p theta tensor p eta. That's what it turns out to be. And the second fact that I'll need is that if you take f and you take its inner product against chi mu tensor chi nu, these are the irreducible characters of Sm and Sn. Their tensor product I can think of as a class function on Sm cross Sn. So these are class functions on Sm cross Sn. But yeah, and that is the characteristic function of f. I have like 3 different notations now. here I have m comma n, here I have m tensor n, and here I have nothing. So I'll make them all m comma n. And here you have s mu tensor s nu. Right, because the characteristic function now goes into the tensor spaces of the symmetric functions. Okay, and one thing, the bilinear form on the tensor space is the product for pure tensors, it's the product of the bilinear forms. Yeah, all this is from definitions and keeping track of how things work for tensor spaces.
No, I mean to say, there is no content to that right now.
No, there's really no content.
There is no content.
I mean, in the sense it's, yeah, there's no trick or anything, it's just. Okay, so now we are ready to do the analog of, get the representation theoretic interpretation of Littlewood-Richardson coefficients. So the thing to look at in this case is you take a partition lambda of m plus n. This is like we're taking a partition lambda of n plus 1. Now we are generalizing it, we're taking m plus n. And now what we'll do is we'll take the character chi lambda and then we'll restrict it from Sm plus n to Sm cross Sn. Okay, and let's just compute this against chi mu tensor chi nu. And for this we'll use the second rule that I wrote. Well, both these rules actually. We have to compute the characteristic function using this formula, and then we compute the inner product using this formula. So if we do that, we'll get, now this is a double sum over partitions of m, sum over partitions of n, 1 over z theta, 1 over z eta, chi lambda, w theta comma w eta. Right, we are just taking a pair now, Sm cross Sn inside Sm plus n. So this is permuting the first m elements, and this is permuting the last n elements. And then, as I said, it should be p theta tensor t eta, and then I need to take the inner product against s mu tensor s nu. Well, I can write that as the sum over theta partitions of m, eta partitions of n, and then 1 over z theta, 1 over z eta. And let me just analyze this part. So this is just p theta against s mu and p eta against s nu. And this chi lambda, this again we can use Murnaghan-Nakayama rule. If you take this element w theta comma w eta and think of it as an element of Sm cross n, then its cycle decomposition is just obtained by concatenating the cycle decompositions of each of these things. So again, the multiplicative way in which power sum symmetric functions are defined comes to the rescue, and we get p theta, p eta, s lambda. And then we have p theta s mu, p eta s nu. Yeah. This thing is just this. Yeah. Okay. Now I'll try to sum over the eta part first. So we'll keep the sum over theta outside. So 1 over z theta. Anybody who doesn't depend on theta, well, there's this guy, right? So oh no, I should take the thing that doesn't depend on eta. So this guy p theta s mu, and now I'll write the other thing inside. So now this of course again doesn't depend on eta, so I'll write p theta times summation 1 over z eta, and then I'll bring this thing inside. That's the old trick. Bring this inside, and here we'll have p theta p eta comma s lambda. No cheating, I hope. Yeah. Okay. So but then the thing is to interpret. I think this p theta I've already taken out, right? No. That p theta has gone here, p theta s mu. This p theta is here, p theta p eta. So I can, okay, let's say I didn't put it here, then I can always pull it out. So that's there. But the reason I pull this out here is because now this is just a characteristic function of a character. So it's a Schur function. P theta characteristic s nu s lambda. Now what I'll do is I'll bring this out by linearity, and I'll say that okay, this is just there, it doesn't depend on theta. But what is this? This is the characteristic function of s mu. That's it. Okay. So thank you. So,